All right, thank you and welcome to What Physicists Do. It's my great pleasure to introduce Dr. Paul Kallis. He's an astronomer at UC Berkeley. He received his Bachelor of Science from the University of Michigan and his PhD from the University of Hawaii. His work has led to groundbreaking discoveries of the environment around nearby stars. So his characterization and discovery of debris disks, and then his obtaining of the first visible light images of an extrasolar planet with orbital rotation. This is around the star Fomalhaut, and the planet is Fomalhaut b. You know, Dr. Paul Kallis has this planet that is his discovery. Just incredibly exciting work. He was the first speaker that I invited to the What Physicists Do series. So I now know how long I've been doing What Physicists Do, because I was like, well, I can't ask anyone I've asked before, right? Because I've just been running this series for a brief period of time, and then I looked, and Paul had been here basically 10 years ago, and I said, oh my goodness. And then I went, oh, I can ask people back. And of course, so I was very excited to ask Dr. Paul Kallis here. And so when I did, he said, that's perfect. Schedule me on this date. And he told me that. And he said, we'll have something to say. And I don't want to ruin it, but there was a brand new press release based on his work. And so we actually have hot off the presses science. So let's give a warm welcome to Dr. Paul Kallis.
Thank you very much, Scott. It's actually a real pleasure to be here. I can't believe 10 years already went by. And I did take your series titled to heart, What Physicists Do. So I'm going to talk about that first discovery that Scott alluded to, Fomalhaut b, and the question of what did I do to arrive at that new discovery. But just last Thursday, we came out with a press release on something we discovered about another planetary system. So I'm going to talk about the hot off the press topic too. So I guess another related question is, where do physicists come from? And like Scott said, I came from Michigan. That's where I grew up. And ironically, it's the cloudiest state in the country, and I became an astronomer. It goes to show you don't actually need to see the sky all the time to be interested in physics and astronomy. I double majored in physics and astronomy at U of M. And then I went to Hawaii, and I lived there for 6 years, because the University of Hawaii has some of the premier observatories atop Mauna Kea. If you've been to Hawaii and the Big Island, that volcanic peak, Mauna Kea, at 14,000 feet, has some of the most advanced observatories available to an astronomer. And then from there, I went to Max Planck Institute. And so as a scientist, this is the wonderful thing, you might find yourself somewhere else in the world, somewhere else very exciting. And in Heidelberg, there's the Max Planck Institute for Astronomy, and their telescopes are in the south of Spain, in Andalusia. So I was a frequent visitor to places like Granada and Almeria and Barcelona on my way to these observatories. Then I went to Baltimore, because Baltimore is where this research center exists called the Space Telescope Science Institute. And it actually employs over 300 people, and their job is to control the Hubble Space Telescope and to develop its science and the technologies needed to keep it one of the most advanced observatories around. And then finally, I came back west again and ended up in Berkeley, where I've been there for the last 19 years. So Fomalhaut b actually was big news, and it appeared in the New York Times. And what you see is this image. And I hope by the end of my talk, you'll actually understand what you see. I mean, at face value, you see this sort of elliptical thing of light, and then there are these black regions here. And what are those things? Why are they there? And I think by the end of the talk, you'll understand what you see. And then I'll, of course, describe what we did after the discovery. So to search for extrasolar planets, there are many techniques available. And the most successful was not direct imaging. Direct imaging is rather technologically hard. The first successful technique was Doppler imaging. Doppler imaging is actually looking at the star and obtaining a spectrum of the star. So even though the cartoon shows the planet is never directly observed. All you're seeing is light from the star, which is being dispersed by a spectrograph, and this star has spectral lines. Because the star itself is orbiting around a common center of mass, it's actually moving back and forth in space, causing a red shift and a blue shift of the spectral lines on a periodic basis based on the orbit of the planet. So from just looking at the star, you can indirectly infer that a planet is moving the star back and forth due to this gravitational effect. And so we can understand how massive the planet was and what orbit it's on, roughly. The next successful technique is transit science, and thousands of extrasolar planets have been discovered using a telescope that's probably famous by now called the Kepler Space Telescope. And the Kepler Space Telescope essentially observed millions of stars. And if the orbit of a planet is exactly edge-on, it blocks a portion of the light coming from the star. Again, you're not observing the planet, you are observing the star. The star has some baseline output of light, and every now and then when the planet transits in front, you see this dip. And from this dip, you can tell a few things. Of course, you can tell what its orbital period is, and you can also tell the size of the planet, because this dip is proportional to how much area the planet blocks. But there is a disadvantage. If you think about it, the orbit of the planet has to be exactly edge-on for this to happen. If the whole system is tilted away from edge-on, the planet ends up going around the star, never actually passing in front of it. The way you solve this problem is you observe millions of stars, and just by chance, thousands will end up having an edge-on orbital configuration. So these are the two indirect techniques. How about a direct technique? So I think the most direct technique, if you think about it, is just go to an exoplanet. Why not go to an exoplanet? Well, we are going to the nearest star systems. There are 4 spacecraft launched many years ago, the Pioneer and Voyager spacecraft, and they're actually departing our solar system. The problem is, even though they're going phenomenally fast, like Voyager 1 is going 60,000 kilometers per hour, 60,000 kilometers per hour, and let me make sure that's right. Yes, kilometers per hour. A bullet goes 3,000 kilometers per hour. So it's one of the fastest things that we've ever launched. Yet, at that speed, it's still going to take 40,000 years to reach the nearest star system. So going to an exoplanet to take an image of an exoplanet is not going to work for all practical purposes. Okay, so if we can't go to an exoplanet, how about imaging an exoplanet? You'd think this would be relatively straightforward. We have a camera, we have a large telescope, and we have the star and planet, and all we have to do is detect that little planet next to the star. Problem is the glare from the star, which in textbooks is often likened to observing, looking straight into the light from a lighthouse. And with all this glare from the lighthouse, you can't see anything faint next to it, even though those faint things may exist near the lighthouse. What you want is a magical trick to turn off the lighthouse. Wouldn't it be nice if we could just turn off a star? If you can turn off a star, then you would see the fainter planet next to it. And it may even help if you could find a way to turn on the planet. This is called the problem of contrast. The difficulty in direct imaging is high contrast. You have a very bright thing next to a very faint thing. If you can diminish the light coming from the star and increase the light coming from the planet, that would solve your problem. So how do you turn off a star? How do you turn on a planet? Turns out we actually do have a few tricks that we can play, and this is how extrasolar planets have been directly imaged in recent years, including Fomalhaut b. I'm going to talk about these three tricks. The first basic one is to use a coronagraph, and I'll explain what that is next. The second is to use the most advanced observatories we have to get the sharpest images possible, either from the space or from the ground. And the third trick is to use infrared light, and I'll explain that as well. So what is this first thing? The coronagraph of Bernard-Liot. Corona is the atmosphere of the sun, and a coronagraph is something that takes a picture of the atmosphere of the sun. However, the solar corona is very faint, and the only way to detect the solar corona is during a total solar eclipse. At least this is the case in the past. In the past, astronomers knew that the sun had this tenuous atmosphere called the corona, and they would calculate the times and places of total solar eclipse, such as something that would happen in India. And they would literally leave their offices, wherever they were, in England or Germany or whatever, and they would travel to India just to observe this total solar eclipse for the few minutes of observations they could obtain of the solar corona. For example, obtaining a spectrum from the solar corona. So this is a problem. You had to travel far, you only got a few minutes of data. And then it was Bernard-Liot, a French astronomer, who in 1939 invented the so-called solar coronagraph. The key to the solar coronagraph is, and here's a picture of a coronagraph I used back when I was a student, and this is just 44 centimeters in length. This is attached to the end of a telescope, basically where the light comes to a focus, except you attach this coronagraph to that focus so that the first thing that hits the instrument is, the first thing that light encounters in this instrument is this tiny, tiny spot. That spot creates an artificial eclipse of the sun. Then in the 70s and 80s, people had the idea that we could also eclipse stars using the same method that solar astronomers had developed. So the solar coronagraph became the stellar coronagraph. It was the key to canceling light from bright stars so you could improve this contrast problem. There is another problem though. The light has to come to a focus on this spot, and the sharper the image, the more light from the star is blocked. Problem is, the atmosphere actually has turbulence and blurs astronomical images. Of course, here I'm just looking down into a swimming pool, but roughly the same type of turbulence occurs in our atmosphere. It's even worse than a swimming pool because the turbulent portion of the atmosphere is actually moving past us due to winds. So if you can imagine this turbulence also moving past your line of sight at something like 25 miles an hour, that is a severe problem of turbulence. So there are two solutions to this problem. To sharpen our images, we can skip the atmosphere, go up into space, and that's why the Hubble Space Telescope is useful. The second solution, which Scott here is an expert with, is to use adaptive optics. Adaptive optics can compensate for this atmospheric turbulence. So in the results I'm going to show, you'll see some Hubble Space Telescope images, and later I'll talk about adaptive optics. Here is the Gemini Observatory, where we have an instrument called the Gemini Planet Imager. And adaptive optics essentially solves the problem by having mirrors that change shape as rapidly as the atmosphere changes. These changes of shape nowadays can happen something like 1,000 times a second. And by doing this, we can compensate for all that turbulence you see, sharpening the images to the same quality you would get from space. Okay, so we have our first two tools. You should know what a coronagraph is by now, and our technique of using the Hubble Space Telescope and adaptive optics. What about this story about infrared wavelengths? Why, just like in any experiment, you have to choose, or you have to make certain choices. And here we're going to choose to observe in the infrared and not in the optical. For example, our eyes see in the optical. There is a reason, one related to the instrumentation and the atmosphere. Infrared wavelengths actually do produce sharper images with adaptive optics. But there is another reason related to the contrast problem. And I can illustrate this with this airport video I shot at a time when there was a flu epidemic, and as passengers are arriving, they're being scanned by an infrared camera. And so here's the infrared image. This is, of course, a very bright daytime scene. So you can see that the optical light here is rather bright. But in the infrared, all you're seeing is the warmth from our bodies. And the reason this is being done is to see if somebody here has elevated temperature, so they can be screened for the flu. The contrast here is quite a bit better than the scene you actually see in the optical. In the infrared, everybody is glowing. There's nothing dark about us. We're glowing hot. And that's why we use infrared wavelengths, because planets are also glowing hot. Even our own Venus. If you look at Venus through one of our telescopes, you see the crescent Venus here. And this is an optical image. But if you look in the infrared, there is no night side. All of Venus is glowing from its warmth. You've now turned on the planet. You've made it much brighter than it is in the optical. You use infrared wavelengths. For example, here's another picture of Saturn, where you can see that if you're looking at 5 microns, which is an infrared wavelength, the entire planet is glowing from its warmth. Okay, so we've got our 3 techniques. The last and final thing to do is to choose your targets carefully. You can have all the tools in the world, but the question is, what do you do with those tools? One reason I chose Fomalhaut is because it was previously known that this bright star, which you can see with the naked eye, it's a first magnitude star, is rather young. At the time, we thought it was 200 million years old. Some revised estimates say it's 400 million years old. And that's considered young for a star. If it's young, that means any planets around it will be glowing, just like what I showed you with Venus and Saturn. Glowing even more than Venus and Saturn are glowing. But as you can see, the closer you get, the problem is you don't see anything. You're swamped with light, and that's where we bring in the coronagraphs. So, looking at Fomalhaut now with the coronagraph, this is my image of Fomalhaut behind a coronagraph with the Hubble Space Telescope. Sometimes people ask me, what do I do? And I say, well, I work with data from the Hubble Space Telescope. And they're like, well, what do? You just get the images, don't you? I go, yes, but the images have to be processed. There are techniques we have to use to clean up the images to find what we're looking for. This is literally what you see when you target Fomalhaut behind an occulting spot. Fomalhaut is so bright, it's actually causing bleeding in the columns here. Fomalhaut is slightly saturated here. And of course, you have all this residual light. So I spend a lot of time trying to remove this residual light using a variety of techniques that can take a while. I might get this image, and it might take me a year to clean up this image. And when I did so, this is what was revealed. It's the image you saw in the New York Times. And now you should understand that the star is actually behind an occulting spot. This black region is because I used an occulting spot. There's some other structures here. These are occulting bars that are different occulting elements in the camera. So these are also things in the instrument that can be used to block stars. And what you see here is an elliptical ring of nebulosity. This is roughly 140 astronomical units from the star. So the star is not seen, it's been blocked. And this nebulosity is extremely faint, 1 billion times fainter. And that's a ring of comet dust. If you trace this belt or ring of comet dust, there's something you might notice. And that is, it's not centered on the star. Why would a comet belt not be centered on a star? Here's the location of the star, and here's the geometric center of this this ellipse that I drew. So this was a hint that Fomalhaut has a planet around it. The only reason this belt should be offset from the star is if there's a planet in the system that we haven't detected yet that also has an elliptical orbit, an eccentric orbit. It's a non-circular orbit. It's not perfectly round. And because the planet has an elliptical orbit, it forces the comet belt to also have an elliptical orbit. Okay, so which object here is the planet? Is it, for example, this thing, this little speck? Is it that one there? Is it this little speck here? Is it any one of these other specks? So we have a series of tests that we perform, and one of them is to just wait a few years and take the image again. If something is associated with this star, it'll move in space with the star. It'll be a common proper motion companion, is the lingo. Stars in the sky are moving. We can't see it with our naked eye, but when we have these sharp images, we can see them moving relative to the sun from year to year. If there's something here that's co-moving with a star, then it's physically associated with a star. If it's not co-moving, let's say this object, then it's probably a background object much farther away from Fomalhaut that's unrelated. And indeed, just a spoiler, this is the planet. That little speck there was discovered to be a common proper motion companion, whereas a target like this thing is actually a star, a background star that does not have the same motion as Fomalhaut. The comet belt is very interesting. We have the same type of dust in our solar system. If you look at the sunset, sometimes you see a faint glow in the west, and this is light that from the sun that is reflecting off dust grains in our solar system. The dust grains actually come from comets. Comets are beautiful. They have this coma and this tail, and all that dust gets released into space and starts orbiting the sun, creating a disk of dust. This is called the zodiacal light. And here's actually Comet 67P from the Rosetta lander, where we can actually see the dust right outside the lander. All that dust is in our solar system. So that's what we discovered with Fomalhaut's dust belt, this complex of dust produced by comets in the system. Well, how about that planet, Fomalhaut b? Here's the first epoch of data from 2004. So here is the wider field, and we're zooming into this little square. Here is that little speck of light, and we discovered that between 2004 and 2006, it moves with Fomalhaut, but it has a slightly offset motion. And that is actually the orbital motion of Fomalhaut b around the star. This video shows, I don't know if it's going to show up, but we've been tracking Fomalhaut b using the Hubble Space Telescope for several years, and you can see that it's moving in the system relative to the star. It's not a background star. There's some background objects in this image. Here's that other background object. Those stars have a different motion, completely different. This is actually a background galaxy right here. This smudge here is a real thing, but it's in the background. Fomalhaut b has orbital motion, and you can immediately see something weird. It doesn't look like it's orbiting Fomalhaut this way. It's almost like leaving the system. It's going somewhere else. It almost looks like it's going to cross over into the belt. So this was actually a problem, because none of this was expected. My colleague Christian Marois in Canada discovered the HR 8799 planetary system. These specks of light, remember this is a chronographic spot, we're blocking the star. These specks of light are 4 planets around HR 8799, which is another nearby star. And these glow in the infrared, as expected. With the Hubble image, I actually used a visible light camera. I used the red filter in the visible light camera. But this is not where we expected to detect Fomalhaut b. When we went to Keck Observatory and Gemini Observatory, we used the infrared cameras on these large telescopes, and we still couldn't detect Fomalhaut b. For some reason, Fomalhaut b is detected only in the optical, unexpected. Moreover, the HR 8799 planets are orbiting its star in nice circles, but Fomalhaut b seems to have a high eccentricity as if it's going to cross the belt. Also unexpected. Here's a nice movie that Jason Wang and Christian Marois made of the planets moving around HR 8799. You can sort of tell that they're all going around the star. None of these planets are moving away from the star like Fomalhaut b. So one of the conclusions people proposed is that Fomalhaut b was not real, that I had made a mistake. You remember in those images, there are a lot of little specks there. How do you know I selected the right speck to say that that's a planet? Could it have been chance that I thought that one speck was the same as the next speck and therefore interpreted this as orbital motion? So we have these problems that invoked a lot of skepticism. First, Fomalhaut b was not at its expected location. It wasn't in an orbit like you would expect. Second, nobody else had actually looked at the data, and there was no independent confirmation. So in all science, replication is of paramount importance. And then finally, the Spitzer Space Telescope, which works only in the infrared, looked at Fomalhaut and did not detect Fomalhaut b at all. It wasn't there in the data. And in fact, this result actually put me in Phil Plate's Bad Astronomy blog. So here is, of course, he wasn't saying that I was a bad astronomer. He was saying that here is a result that was unexpected. Here is this Spitzer Space Telescope infrared image. Fomalhaut b should have been detected here. Here is a model of what should have been seen, but in reality, nothing was seen. So these astronomers who published this Spitzer image said Fomalhaut b is spurious. It's a false positive, as we say. The public, of course, was very disappointed. Here is one of the comments that was related to that blog. Man, I thought Pluto had problems. Another person, though, understood what the paper was saying. Every observation we have is sensitivity limited. We have a certain sensitivity to a phenomena. So this person says the planet still hasn't been ruled out. That's because the more massive the planet, the more it glows and the brighter it is in the infrared. So the more massive and the younger it is, the brighter it is. In the case of the Spitzer data, what was really shown is that Fomalhaut b couldn't be more massive than 2 Jupiter masses. That model that was depicted there showed a planet that was 2 to 12 Jupiter masses. But if Fomalhaut b was less than 2 Jupiter masses, let's say it's just like our Jupiter, that observation would not have been sensitive enough to detect the infrared light from Fomalhaut b. In other words, this absence of new evidence was not evidence for the absence of Fomalhaut b. It just established a limit to its mass. So we can cross this up, no problem. How about this thing? No independent group had replicated the discovery. Well, Hubble data are actually public. You can actually request my data right now and start working on it this evening if you want on your laptop. And that's what 2 different groups did. They didn't ask me for permission. They didn't consult with me. They just went to the Hubble Space Telescope archive and independently from me and actually from each other, they published 2 papers where they confirmed the existence of Fomalhaut b in the Hubble data. So the second thing should be crossed out. And how about this problem with that it's not at the expected location? Well, it just so happens that Fomalhaut B has this highly eccentric orbit. We kept tracking its orbit over many epochs, and in fact it looks like it has an orbit that is going to take it past the ring, and then it comes back down close to the star, and then it loops back up past the ring. We did an analysis of its orbit, and here are the orbital elements, which are very fundamental to astronomy. You have the semi-major axis, which is 177 AU. Remember, the dust belt is roughly at 140 AU. It has a high eccentricity. It's highly non-circular, eccentricity of 0.8. The little q and the big Q represent periastron and apastron. Periastron is the closest approach to Fomalhaut, the star. Apastron is the farthest Fomalhaut B goes from the star. And its orbital period, P, is 1700 years. And the mutual inclination of Fomalhaut B with the belt may be something like 17 degrees. So here's an edge-on view of the system. It's possible that the orbital inclination of Fomalhaut B is tilted relative to the belt by 17 degrees.
Are all those different things, different possibilities for the orbit?
Yeah, yes, indeed. Yes. So, those different. The question was, what are these different lines? So we have some uncertainties in our measurements, and these are all the different possibilities for Fomalhaut B's orbit. And that's reflected in these in the so-called errors. So why is that mutual inclination important? Well, one of the complaints was that if Fomalhaut B is going to cross through the belt should not exist. The mass from the planet should gravitationally destroy the belt or otherwise perturb it. But it turns out if the plane of the orbit, here is what Fomalhaut B sees as it comes through periastron. If the plane of the orbit is tilted, it actually never encounters the belt. So here is the face-on view. Here is the orbit of Fomalhaut B, which looks like it's crossing the belt. See, here's the orbit. It looks like it's crossing the belt. But because it has an inclination, it actually comes through from the top of the belt and exits from underneath the belt, sort of like two links of a chain. Okay, so Fomalhaut B is puzzling. Yet, this is what nature has for us to study, and it opened up many new questions about how Fomalhaut B ended up in this orbit. And this is going to tie into the last part of my talk, where we talk about passing stars. There was one last mystery that I haven't talked about yet, and then why did we detect Fomalhaut B in the optical and not in the infrared? So what we proposed actually in 2008 is that we don't see Fomalhaut B directly. What we see is a circumplanetary dust ring. In fact, this circumplanetary dust ring is much larger than any of the rings around Saturn. And it was somewhat of a risk for me as a scientist to propose this, because what I calculated is the ring had to be between 16 and 35 planetary radii. And this is not observed around Saturn at the time. A ring system that large was not known to exist in nature. But as it so happens, the year after I published this, somebody discovered a huge ring around Saturn called the Phoebe ring. So in this diagram here, this is the familiar rings, the main rings of Saturn that you can see through a telescope. All of this is actually a zoom in of a region right in there. Phoebe is a satellite at 215 planetary radii. Phoebe orbits Saturn, and it gets bombarded by meteors. Each impact on the surface of Phoebe releases dust that escapes Phoebe and starts orbiting Saturn, so that Saturn actually has a ring that's much larger than anything I had proposed for Fomalhaut B, the Phoebe ring. So there was no problem now with this ring hypothesis in terms of proof of concept. So to summarize, we have Fomalhaut B, which is definitely real. It's been replicated, probably more so than any other result in extrasolar planets. And we think, my theory anyway, is that it's what we see is reflected light from a circumplanetary ring. Of course, we want to find other examples of planetary systems using direct imaging. And this is where we've been successful using adaptive optics. I've been involved with something called the Gemini Planet Imager, which has been installed in the Gemini South telescope in Chile. And this is an 8-meter telescope. We've been working on this instrument for the last 10 years. It was actually commissioned in 2014. So actually we started working on it in 2004. And what it does is use the latest technology in adaptive optics in order to correct the atmosphere, coupling it to the latest technology of coronagraphy. So we can sharpen our images and block starlight. And of course it works in the infrared. And we used to go down there for our observing runs. This is what physicists do. We have to go to sites and do our experiments. Here is sunset in the Chilean Andes. Lots of people provide photographs of the local wildlife. It's rather beautiful. Another way to do our experiment is to work from here in California. So we can set up AV systems, sort of like whatever, Skype, and actually control the telescope from Berkeley. So here is a video I took when we just started commissioning GPI. These are the offices in Berkeley in the astronomy department. And I'm walking from my office to this little remote observing nook. Here are people controlling the telescope. And here we're exposing on a star called HR 4796A. And this system is so sensitive and its performance so astounding, I would say, that we can actually, without any processing, see a planetary system in a raw image. Here the star is being occulted by an occulting spot. And before we do anything else to the image, you may be able to see a faint ring. Can you see that? That is a comet belt around HR 4796A. That comet belt is 80 astronomical units away from its star. Our Kuiper belt is 40 astronomical units from the sun. So this is roughly twice the size of the Kuiper belt. And we can see it in real time. Really amazing. You can do the post-processing and then you come up with an image like this. It's a really fantastic thing. Now you should, of course, understand that the star has been canceled and blocked by the chronograph in order to reveal the belt. We were looking for planets, and we have not detected a planet around HR 4796A. This doesn't mean the planet doesn't exist. It means we have a certain sensitivity to a planet at this age of roughly 2 Jupiter masses or greater. There should be a planetary system in this middle, in this evacuated area, but it's possible the planets are less than 2 Jupiter masses, and we just need a more sensitive camera and instrument, such as the 30-meter telescope or the James Webb Space Telescope or something like that, that will come online in the future.
Has an indirect method been found with that particular star, like Doppler?
So the question is, has an indirect method been used to place limits on a planet around HR 4796A? And the answer is no, actually not. This type of star is actually difficult to get a spectrum of. It's an A star, and its spectral lines are broadened and will not give you as accurate a result as you desire, as can be achieved with lower mass stars. Here's one planet that we did discover with the Gemini Planet Imager, and this was actually rather exciting. Here is the little dot. Again, these little dots are whole worlds, in this case, roughly 2 Jupiter masses. The star is not seen because we've canceled it. And its separation is roughly 13 astronomical units. So this is exciting because now it sort of sounds like our solar system. Fomalhaut B is very far out from its star at something like 130 AU from its star. 51 Eridani in the constellation Eridani is now very close to our own Jupiter, and roughly the same distance from its star as our gas giants are from the Sun. So what do we do? We're using the Gemini Planet Imager to survey many stars. We've actually gone to almost slightly over 500 stars. 51 Eridani is our major discovery. Here is what we do when we're going down to Gemini Observatory. So we're not in Berkeley, we're at Gemini Observatory in one of the control rooms of the telescope itself. We have a large team because there are many things that go into obtaining these images. It's not just the single astronomer in the middle of the night taking photographs. We've got the telescope operators here. So these 6 screens are controlling the telescope and all the things that have to go right with the telescope. Here, this monitor is actually an AV system where we're directly connected to people at Stanford and Cornell, because this has actually many institutions involved. So they're helping out. Over here, we're controlling the adaptive optics system, and there are 2 people here. And then in real time, this person is analyzing the data to see if we're getting the best data possible. And if not, that person communicates to this person to change something, to tweak some of the settings in order to get better data. And this person as well is in charge of analyzing the data in real time. And of course, over here, actually Rob DeRosa, who I'll mention in a minute with our press release, he was in charge of our target selection software. He wrote it, actually. And this was really critical, so you know out of 500 stars, what are you doing next? You just don't pick random stars. You choose the best star for observation next. Even though we discovered 1 planet, 51 Eridani, we actually imaged many, many more of these comet belts. Here's a sort of an image gallery. Here's HR 4796A right here. This was originally discovered by the Hubble Space Telescope, actually. These red boxes show new discoveries. And I'm going to talk about HD 106-906. This was a new discovery, and this was the subject of our press release on Thursday. So I'm going to start talking about HD 106-906, which was actually very mysterious. This video is actually on YouTube, and I thought I would just go through the video and you get sort of my voiceover instead of the music that's on the video. So 106-906 is a southern target. It has to be a southern target because Gemini South is in the south. So this is not observable from our observatories here. And right now you're actually looking at a Hubble Space Telescope image that I obtained after we discovered it with the Gemini Planet Imager. So this image should now make sense because of the things you learned. This black region is blocking the star, and our French collaborators actually discovered the star is a spectroscopic binary. So it's not a single star, it's a tight binary. And these are background stars. One of these is a planet. And remember, the way we confirm it's a planet is if it's moving with the star in space. And what you see here is a disk of comet dust, which is rather puzzling because of its huge asymmetry. Let's see this. And scale as well. So this scale bar is 500 astronomical units, and this is easily the size of the disk here. But note that the southeast side of the disk, in astronomy, north is up, east is left. The southeast side of the disk is truncated, as if it's been cut off. Whereas and also it's rather vertically puffed up. This nebulosity is real. So we have this lopsided disk, which is long and thin on one side and puffy and short on the other side. And the way to do this, as I mentioned with Fomalhaut, is through a gravitational perturbation of the whole system. Meanwhile, Vanessa Bailey and collaborators discovered that this point source right here is actually a planet. And this is puzzling too. First of all, the planet is 738 astronomical units from its host star. Planets don't form at large distances from stars. Planets form, the place they are born is in the flat and relatively dense disk of dust and gas that orbits a star. The disk is here, but the planet is now found over here. And this is a 15 million year old system, so it's rather young. How did the planet end up forming in a disk, if it really formed in a disk, and end up here 15 million years later? So when we published our results, I came out with some ideas. One idea is that there is another planet in the system that we haven't discovered yet, and that planet kicked out this planet. They basically encountered each other violently, and one planet flew out into interstellar space practically, and that's why we see it over here. Another idea is that maybe a passing star encountered the system. So another star could give the entire system a strong gravitational kick. And that gravitational kick could disturb the dust disk and perhaps cause the planet in the system to come out to a farther distance from the star. So those were just ideas back in 2015. How do you test your ideas? Well, fortunately, there are many projects that are making available exquisite data. And one of these projects is called the Gaia Mission, which has just been delivering a new set of data for the positions and proper motions of all stars. Not all stars, for the brightest 1% of stars in the galaxy, which is significantly more than what we had in the past. So if you have position and proper motion, and as well as radial velocity, you can trace the three-dimensional motion of stars relative to each other. This is something we didn't have in 2015 to this accuracy. So this is why this result is new. The Gaia mission gave us this new data set, and we could check if any one of these other stars passed by 106, 906 in the recent past. Actually, we checked 461 stars. So we took this sample of 461 stars, and it turns out that 459 of them were nowhere near 106, 906 in the past, except two. And we found those two. Oops, shoot. Now it's starting from the beginning again. I'm just going to go to the next slide. So here's what we think happened. This theory, this first part was developed by a theorist in Grenoble called Laetitia Rodet. And what she thought happened is that once the central star was discovered to be a binary, she assumed that the planet formed in a disk, and this scale bar is 3 astronomical units. So it's very close to the star. Because the planet is encountering material in the disk, that material can slow down a planet and cause it to actually spiral in towards the binary star. At some point, the gravity of this binary, which has an eccentricity of roughly 0.6, can cause the planet to obtain a very unstable orbit. That instability then scatters the planet outward to a highly elliptical orbit away from the star. But there's a problem. Every time the planet comes back in towards the binary system, it receives an additional kick, and then an additional kick every time. So that after roughly 10 to 100 kicks, the planet should be lost to interstellar space because the binary keeps kicking it with its gravity. So the planet should not be there today. It should have been kicked out of the system. It should have become an interstellar object. Maybe you've heard of Oumuamua. which was recently detected around the Sun. This is an interstellar object that's been kicked out of a planetary system somewhere else in the nearby universe. One way to solve this problem is to have a passing star. The passing star also has a rather strong gravity, and it can give a kick to the object so that instead of having a close approach to the binary, the orbit becomes such that the periastron moves beyond this unstable zone around the binary. Okay? So without a passing star, you have this orbit here. The orbit keeps encountering the binary. This red circle represents the unstable zone. If the planet keeps entering the unstable zone, it will be kicked out into interstellar space. But while the planet is here, and actually in a very elliptical orbit, planets spend most of their time very far from the star. If the planet is here and a star happens to fly by it, it gives a little kick to the orbit of the planet so that it now never sees the binary as closely as it did before and becomes long-lived. That's why we observe it today. This was the theory presented 2 years ago. So the question was, is this really true? Is this really true? Are there perturbing stars? And we did find 2 perturbing stars. This is sort of the more technical way to show what we discovered. What we're plotting here is a distance of closest approach here in parsec. And this is back in time. So closest approach time in millions of years in the past. And we have these, we propagate the uncertainties in the measurements. And we can show that these 2 stars approached within 1 parsec. This is half a parsec, this is 1 parsec. So these 2 stars approached within 1 parsec of 106,906 between 2 and 3 million years ago. So that is the result. What I really liked about this project with these new Gaia data, is that we could also calculate the angle of approach, which was much harder to do any time in the past. So we calculated the angle between the disk and the flyby. If the flyby is actually coplanar with the disk, it has a stronger gravitational effect on the system. And lo and behold, not only were these the closest perturbers, these were also very close to coplanar with the disk. 0 degrees would mean that it's exactly in the plane of the disk, and 10 degrees is 10 degrees away from the plane of the disk. And these perturbers are roughly 5 degrees away from this plane. Let's take a look at how this compares to our solar system. You can play the same game with our solar system. You can calculate which stars had the closest approach to our own solar system. And that's been done. Eric Mamajek, friend and colleague at the Jet Propulsion Laboratory, calculated the closest approach of Schultz's star to the Sun. 70,000 years ago, this star, Schultz's star, which is actually very low mass, it's 0.15 solar masses, actually came within our Oort cloud of comets. That's shown here. By passing through the Oort cloud, it's possible that Schultz's star delivered some comets into our inner solar system. And here's the HD 106,906 system for comparison and to scale. We don't know if there are any planets within its dust belt. We see the dusty debris here, and here's 106,906 out beyond the boundary of the dust belt. And here are the 2 passing stars, which we think may form their own physical binary. So just to make things super complicated, you have like a binary here and another binary passing by the binary. And these 2 stars together are rather massive. If you add up their mass, they're 2.7 times the Sun's mass. So they may have had a strong effect on the system, which needs to be worked out by future work, actually. So how is this relevant? Flybys are relevant to our own solar system One of the mysteries, for example, is why does Sedna have the orbit it has? Sedna is a distant Kuiper Belt object. And the orbit here is drawn with this yellow arc here. The sun is there. The orbit of Neptune is that right there. And how is it that Sedna never approaches the gas giants and the ice giants? Sedna's orbit, its closest approach to the sun is far beyond the orbit of Neptune. Like I just explained, passing stars can influence the orbits of these objects so that they become detached from the planetary region. And the same is true for the hypothetical Planet 9 that you may have heard of. Why is Planet 9 out at this distance where it's hard to detect? And why have we never seen Planet 9 in our own solar system? It's the same process. If Planet 9 exists, it could be that, just like with 106, 906, it formed very close to us, for example, where Jupiter is. But Jupiter gave it a kick to a highly eccentric orbit, and then passing stars actually detached the orbit of Planet 9 so that it never comes close to our planetary system again. And here's another example of why this is relevant. This is an artist's sketch of what Oumuamua might look like, this sort of lopsided object that passed by our sun on a hyperbolic orbit, so it's not bound to our sun. And of course, there's been speculation that this is a spaceship. But really, that's the worst explanation, because the best explanation is that when you have these gravitational perturbations of stars on planetary systems, you can really release a lot of material into interstellar space. So what does such a encounter look like? Here is a simulation I did back in 2001 with another collaborator from England, John Larwood. And what he is the expert in doing these theoretical simulations. And you have a disk of particles here. And we're going to now pass a star very close to this disk, much closer than what we've been talking about so far. So you have, did you see what happened? This object came on a parabolic flyby, and it basically destroyed the outer part of the disk. All of this material is now going out into interstellar space. And of course, another nice thing about flybys is that they can send comets from the Oort cloud back into the solar system. And here's a solar coronagraph. So again, now you know what we're showing here. This is a coronagraphic spot that is blocking our own sun. This is a solar coronagraph. And over time, you can see comets come close to our solar system. And the reason is that the gravitational perturbations of passing stars can reinsert distant objects into orbits that pass near the sun. I was thinking of ways to write this out, but I thought Carl Sagan really, his writing is just so fantastic, I just decided to quote him right here. How he explained how comets from the Oort cloud end up being pushed into our solar system by passing stars. So what's next? There's a lot of excitement about the James Webb Space Telescope. And if you look at this image here, here's the Hubble Space Telescope. Its mirror was only roughly 2.4 meters in size. This may be roughly the diameter of this desk in front of me. But the James Webb Space Telescope is going to be have a mirror diameter of 6.5 meters. And it's actually an infrared telescope instead of a telescope like Hubble, which operates from the optical to the infrared. You can see some big differences here. The Hubble Space Telescope is in orbit around the Earth. The James Webb Space Telescope is in orbit around the Sun and actually will be quite far from the Earth-Moon system. Why is that? If you want to make a telescope sensitive in the infrared, you have to make it as cold as possible. So the telescope has to be far from warm things. The Earth is actually rather warm in space. So this telescope is going to be far from the Earth and the Moon. And moreover, it has the mirror here is in the shadow of a shade. This material here, which isn't showing up very nicely, is the size of a tennis court roughly, and it's blocking light from the sun from hitting the primary mirror of the James Webb Space Telescope. That means the mirror is going to be about as cold as it can possibly get in our solar system. And James Webb will have a lot of coronagraphs. So when I think about Fomalhaut B, and what is it exactly, I think the James Webb Space Telescope is going to answer that question because it's going to be much more sensitive than anything we've had in the past to the infrared radiation from an object like Fomalhaut B. All right, so here's my last slide. Too long, didn't listen to that guy's talk. So at present, we have this amazing instrumentation to directly image extrasolar planets. And why are we doing that? Well, because in the future, we'll have to know where we want to go. Thank you very much.
Let's see, we made it to 5, so those of you who need to leave, please do so quickly and quietly. The rest of us, we're going to stay for a 15-minute question and answer session. So if you need to leave, please do so right now, quickly and quietly, and I think we'll get started with questions. All right? Paul, you want to pick and choose?
Yeah.
All right, what's your best guess as to when Webb might finally get launched?
Oh, so, well, that's a good way of putting it. The question is, when will the James Webb Space Telescope be launched? There have been delays, and I have emails when we're talking about the fact that right now we will be observing with the James Webb, but in fact it's been delayed to 2020. So not too long.
I thought it was later than that.
It may be, and then maybe a little later than that. Yeah.
All right,
So
that's the earliest we can hope for. Isn't it?
That's the earliest. And it goes to show that in our business we have to have some patience and endurance.
Especially with
you-
space-based stuff.
Especially with space, but also, with the Gemini Planet Imager, that was not too different. I mean, if I look back at my older emails, we were supposed to be on Sky with the instrument in 2010, but really got there in 2014. So this is challenging, and you do need a lot of perseverance to get these projects going. Yeah, go.
So, when you were talking about cleaning up your images from the Hubble Space Telescope, after responding to people's questions of what you do, you said it takes up to a year sometimes?
Yes,
or
that's
at
right.
least in that set, it took you a year. Can you describe a bit about what it means to clean up the image? Is it just reducing noise and improving the signal from your...
Yeah. So the question is, what do we do to these images to clean them up? What exactly is this processing? And there are techniques developed. I'm going to try to find a slide that may illustrate this better. Well, let's go back to this original, to what we show here. Oops, sorry, that's not showing up. So the question is about this slide here, where we go from having all this light to canceling all this residual light. And I'm just going to talk about one thing we do, and there are many other techniques. Well, it doesn't show up here, but if you look at the edge of the frame, and this may still not show up because if you look at the edge of the frame, what we've done is we've rotated the whole telescope. And we've rotated the whole, you can turn on the lights, it's not going to show up anyway. We've rotated the whole telescope around the optical axis. What happens is this residual light here is due to the telescope optics, not the sky, not the universe, not the astrophysical scene. This is a screen of noise due to the optics of the telescope. If you rotate the telescope, the astrophysical scene is rotating, but the noise is not rotating because it's fixed relative to the optics. So in some of my images, I do 18 rotations so that this noise screen is always fixed, but stars and everything else around the star are moving. So now we've separated the astrophysical scene from the noise in the telescope, in principle. And therefore you can subtract it out. And that's how you end up deleting all this light. Oops. You end up deleting all of this light by playing this trick. And of course you have to process these rotations. And this is actually one of the key techniques we use, even with ground-based observatories, we call it post-process. We post-process the data because the data have been obtained at many, many angles. So you can imagine what this post-processing is. You have this light here, but the astrophysical scene has rotated. You need to de-rotate the astrophysical scene and then stack the images, for example. Yeah.
Say you were on a planet in, say, Andromeda, and you had all of your current technologies, and you had a great edge-on view of our solar system. I'm imagining using your 3 techniques, you could probably pick up Jupiter pretty easily. Could you pick up something like Earth or even Mercury, which is smaller and closer to the sun, using your adaptive technologies?
Oh, that's a good question. You know, if we were an alien species on some other planet, I actually really like questions like this. Could we detect us? And so using the Doppler technique, there's a certain thing, a problem here, which is the age of the astronomer and their career. So what you actually want is a Jupiter very close to the star, let's say, like where the Earth is, so that in 365 days you see one wobble. But if you're farther out in the solar system, those, like where Jupiter is, these orbital periods are much longer. So you have to wait a lot longer for these spectral lines to shift. And of course that's possible, you just have to wait longer. The question, so it would be hard to detect Jupiter around the sun, but it's possible if you wait long enough using the Doppler technique. If you're exactly edge-on, you may be able to see the transit of probably Venus and Earth. But to be honest, other people have done the calculation, and I've never done it, so I can't tell you what that transit signal is and which telescope would detect it. Could you do it from a ground-based telescope, like the ones we have on college campuses? Do you really need the Kepler telescope, or do you need, for example, TESS? I'm not quite sure. TESS is the next generation of transiting telescope projects. Yeah.
I'm guessing that in order to have the best probability, if you're using your techniques to discover an exoplanet, you're looking through many of the other hundreds of candidate systems that have already been established by the indirect methods, but without they identify the probability of there being an exoplanet, but they haven't imaged it. So is that what you look through?
Oh, that's an excellent question that actually digs into some of the details that I didn't have time to talk about. The transit and Doppler techniques actually image stars that are relatively old, like 2 billion years older, or 2 billion years or older. Sort of like our sun, 4.6 billion years old. If you remember that thing about infrared light, planets are brightest when they're youngest. So we actually look for glowing planets around stars that are less than 1 billion years old. So the two samples don't overlap at the moment. How do you get them to overlap? If we can improve our technology, we can actually start detecting glowing planets around older stars, the same stars that the Doppler and transit techniques are targeting. And in fact, the goal is to actually see planets in reflected light. There you don't care about how warm a planet is. If your technology can detect the much fainter light that's reflected off a planet, then we can actually look for the planets that are detected through the Doppler and transit techniques. That's when the overlap will occur.
I'm surprised.
Yeah.
I had a question about given our sun, let's say that alien observer is able to detect only by the Doppler, but there are 8 planets tugging on that star. Does that add the, this is a pretty simple view of the red shifting and blue shifting, but if you got all planets all over the place simultaneously tugging, how does that affect this Doppler appearance, so that it could be actually discerned?
Well, that's a good question, which touches on a very interesting technique people actually use. Your question was, well, you're assuming that Jupiter is tugging on the sun, but what happens when Saturn and Uranus and Neptune are also tugging on the sun? Doesn't that mess with the signal that you can see in these spectral lines? And it turns out it does, and that's how people discover more planets. You can see that if another planet is in the system, it may delay the shift of these lines. And also with the transit technique in particular, if you have one planet transiting the star, and a second unseen planet exists nearby that never transits the star, it still has a gravitational influence on the planet you do see transiting the star. And this is called a transit timing variation. The timing of, if you have a single star, if you have a single planet around a star, its timing should be like clockwork, always transiting at the same time. But if you have another planet perturbing ever so slightly that planet that is transiting the star, the timing will be off, and you can infer the existence of other planets. Thank you. That's a good question.
Going back to the bright image you had, with which you had to do a lot of noise reduction, so you said that essentially you do see the shift of the center of that elliptical path here. Well, they're also shifting in the other direction as well, because it appears that your planet is really sort of in the lower, like right corner. So do we also have some vertical shift as well?
Oh, that's actually possible too. Let's say the planet is not coplanar with the disk, that it's slightly tilted to the disk plane. It will actually excite vertical motion in the comets. We can see this around another disk, which is edge on, called the Beta Pic debris disk. Beta Pic happens to be exactly edge on, and collaborator in France, Anne-Marie Lagrange, actually discovered a planet called Beta Pic B, which is tilted relative to the disk. And we can also see that this disk has a warp in it, because a vertical warp, because a planet, if it's not perfectly coplanar, if it's tilted, will also excite the vertical motion of particles in the disk.
For Fomalhaut B, what's the piece of data that you would most want to go back and examine your ideas? Like,
Yeah.
What are you most excited for to kind of lock down Fomalhaut B?
Yeah, so that's a great question. What data am I most looking forward to? And it would be the James Webb program to image the Fomalhaut system. I'm not the principal investigator, actually. This is something that others are going to look at. And the idea is that with this enhanced sensitivity to infrared wavelengths, we can maybe push down our sensitivity to a Saturn mass. So I mentioned that my working hypothesis is that Fomalhaut B is something like a Saturn with a large ring around it, except current infrared technology cannot get down to a Saturn mass in infrared sensitivity. James Webb could.
Well, let's thank our speaker again.